Hey everyone, welcome to homework 3.16. So this first part right now is really important that you read over carefully. I'm not going to read the whole thing to you because you are all capable of reading. But the key point here is that if we are increasing or decreasing something by a certain percent repeatedly, we have to consider the new amount, which means that we can't just add percentages together and say, oh, now it's 50% off. That's not how these percentages work. So if you take a discount, for example, and then you take another discount, you need to take the first discount first. You can't just add that percent decrease together. Similarly, if you're adding interest, you can't just add the interest percentages over time. You will need to take a different look at it because you're going to be increasing based on the new amount, based on that increased amount. And when this happens, if we're taking a percent increase on an amount that has already had a prior percent increase, this is called compounding. And so that's why today we talked about compound interest. So there is also this example of an account balance, and an account that earns 2% interest every month does not actually earn 24% interest a year. So they give you this example of a savings account with $300. And in this case, if they were to calculate using this, right, here's our factor, we're growing by 2% each month, and then we have 12 months, so they put that 12 there. The amount that we end up making, right, is going to be multiplied by 1.2682. So that means the account is actually growing by 26.82%, not just 24%. That 24% is too small for the amount of interest that we're actually getting. So this rate is called the effective interest rate. It's the actual effect. Think of effective as the effect that the interest has on the money. The 24%, when like a company says you have a 24% nominal interest rate, nominal comes from the term nom, which means name. And so it's the interest in name only, right? It's not how much interest you're actually getting or how much interest you're actually paying in some cases. It's the named interest. So it's the interest that they're giving you as a name. Nom can also refer to law or legal. So you could also think of it as like just the legal stated published rate, but it's not actually what you're going to be getting, because that 24% is going to need to be broken up over those 12 months. So why can't we just multiply 25% by 2 to find out how far she'll be running after 2 months in this first scenario for the running? And that's because she is increasing the distance. Oops. What happened to my pen? Hold on a second. There we go. Okay. She is, I believe let's double check. She is increasing her running based on a new increase. And then, does compounding interest make your total greater or smaller? It makes your total greater. So whether it's greater that you owe or greater that you're getting, the compounded interest makes the overall amount greater. What is the effective interest rate? What is the nominal interest rate? So effective interest rate is the actual interest rate for a period of time in which the interest has been compounded. And then the nominal interest rate is what they publish as the interest rate. But it is an interest rate that needs to be broken up over time. How is the effective interest rate different than the nominal interest rate? So the effective interest rate is the actual increase versus the nominal is just what they say it is before it has been compounded. So let's look at some homework examples, and then we can get into looking at how this actually functions. So automobiles start losing value or depreciating, this is an important word, as soon as they leave the car dealership. This is true. 5 years ago, a family purchased a new car. If the car lost 13% of its value each year, what is the value of the car now? So $16,490. If it's losing 13%, then what remains is 87%. So our factor is 0.87. And this is to the value of 5 because we're talking about 5 years. And it is its value each year. So we're not worrying about months or anything like that yet. We're thinking about just years. So 16,490 times 0.87. Oops. 0.87 to the power of 16,490. I forgot to put the calculator up. Sorry about that. Times 0.87 to the power of 5 gives us $8,218.96. So you can see that that amount has decreased quite a bit over time. Okay. Number 6, the number of trees in a rainforest decreases each month by 0.5%. The forest currently has 2.5 billion trees. Write an expression to represent how many trees will be left in 10 years, then evaluate the expression. So 2.5 billion is 2,500,000,000. Yep. And that is times, it's decreasing by 0.5%. Okay, 0.5% is a very, very small amount. That means what remains is 99.5%. So 0.995 is how much is left of the rainforest in those months. Then it says, write an expression to represent how many trees will be left in 10 years. So this is each month, and we're talking about 10 years. So 10 years in months will be 120. And then you can go ahead and evaluate the expression. So in this case, you can go ahead and put that into your calculator to make sure that you have that as an accurate number. So you are responsible, and I'll know if you listened, for filling in that amount there. All right, from 2005 to 2015, so 10 years, a population of pea lions is modeled by this equation, where T is the number of years since 2005. How many lions were there in 2005? So we can see this in our starting amount, is 1,500. Describe what is happening to the population of lions over this decade. They are, so because we're multiplying by a number that's less than 1, they are decreasing by 2%, or you could say 98% remains each year. It says about how many lions are there in 2015. So if we're calculating from 2005 to 2015, we would replace T with 10. So again, you go ahead, use your calculator, calculate that, and find out how many lions are there in 2015. All right, number 8, a bank account pays 5.5% interest. Very small amount of monthly interest. If $500 is put in the account, what will the balance be at the end of 1 year, assuming no additional deposits or withdrawals are made? So in this case, you're getting money from the bank. Now remember to turn this into a decimal. We're going to move our decimal point over 2. So we're going to do 500. We're increasing, so times 1.005. And then this is to the power of 12 because we're talking about at the end of 1 year. What is the effective annual interest rate? All right, so if we want to find that effective annual interest rate, in this case, we're going to look at this right here. So 1.005 to the 12th power gives us, oops, let me change that, equals 1.0616. This means that my effective interest rate is actually let me make sure. Yes, 6 point. I'm going to go over 2, so 6.16% is the effective annual interest rate. That's actually how much. Now, if you wanted to also see that calculated, you can take a look at 500 times 1.005 to the 12th power gives you 530. So that's how much you would make. So 530.83 minus 500, which is the original amount, means you would make interest of about $30.83. If we divide that by 500, you will also get 0.0616, and so that is our 6.16%. That's the actual interest rate that you're going to get over that period of time. It says, is the effective annual interest rate more or less than 6%? So it is more, right? The nominal interest rate would be if we got that 0.5% every month for a year, we would get approximately 6%. But because it is compounding, it's going to be more than that nominal interest rate. All right. Number 9 is a bit of review. It says which equation matches which graph. So we're looking at increasing graphs, right? These are growth factors. And so we're looking for this highest one would be y equals 50 times 2.5 to the power of x, because that's our greatest factor. Our middle one then would be in between there, y equals 50 times 2 to the power of x. And C, then our lowest graph that's increasing the slowest, would be 50 times 1.5 to the power of x. All right, number 10, a major retailer has a staff of 6,400 employees. After the holidays, they decrease their staff by 30%. How much will they have? So you can write this as 6,400 times 0.7, because that's how many will be left. And you'll get around 4,400, a little bit more than that. I'm going to have you fill that in so I know that you calculate it yourself. Or you could also do 6,400 minus 6,400 times that 30% that they're losing. You'll still get the same number, but again, this is taking the starting amount and then subtracting the percent that we're losing there. Number 11, Antoine had a summer job and saved $1,000. He put his money in Capital One Bank, which pays him 10% of the amount invested compounded annually. That's a big percent. Observe the table, what is happening each year. So write a formula that you could use to determine how much interest he gets after any T number of years. So this is 10% of the amount invested compounded annually, meaning per year. So we're not looking at a monthly interest rate, we're looking at a per year. And it is increasing each year by a factor of 1.1, right? So if we were to write this formula then after T years, we would write it as, we have to go backwards to the original amount, which is $1,000 times 1.1 to the power of T, and we can write this as a function equals f of, not x rather, but T. All right. Number 12, Mr. Lee wants to buy a motorcycle. He saved up a lot of money, but he still needs to borrow $200 from the bank. The bank charges 4% compounded annually. How much will he owe if he waits 1 year to pay back the loan? How much will he owe if he owes 2 years, 3 years, 4 years, 5 years? Write a formula to show how much he owes after T years. So the original amount that he needs to borrow is $200. The bank charges 4%, so 1.04 is our factor. It's how much it's increasing by annually. All right, and so after 1 year, right, he would owe 200 times 1.04, which is $208. After 2 years, it would be 200 times 1.04 to the second power. All right, and so then we would take 208 times 1.04 and we'll get $216.32. That's for 2 years. So then you're going to check 3 years, 4 years, and 5 years. And so you should go ahead and add those three. How much is it for 4 years? 3 years, 4 years, and 5 years. Okay. And remember, a key hint to helping you do this is also if you were to look in your graphing calculator, right, you can look at the table to find. Sorry about that little interruption. So let me show you what I mean. So in your graphing calculator, if you go to y equals and you plug in, not 5, that's incorrect, 200 times 1.04 to the power of x. And then we hit second table. We can see how much that cost is going to increase each year. So after 1 year, it's 208. After 2 years, it's 216. 3 years, 4 years, 5 years. So you can calculate them each separately, or you can also use this table. That is a handy way to get those answers. You should know how to do it both ways because we want to make sure that in the case of you not being able to use a graphing calculator, you know how to do it. So for example, if we were to do 5 years, this is what that should look like, okay? That years place is happening here. Now again, in this case, it's annually, so it is talking about years, not months, which is why we can go ahead and put that just straight up number of years there. All right, that's it for your homework tonight. If you have any questions, feel free to reach out. You know how to reach me. Your code word for today is gold bears. Gold bears. Happy homeworking and see you tomorrow.